Hello, welcome to this lecture lecture tutorial number 7. So today we will discuss about whatever is asked in assignment number 6. And as we come to the all lectures from 1 to 6, what we see that we have derived from the uh, uh, we started from the two body problem where we see the excitation, and after that for how the perturbative Hamiltonian determines the excitation of a molecule from in two states. After that we expand it to n number of states and derive that probability of transition. Now when we derive the probability of transition, there's one term is come, it's like transition dipole moment. Based on the transition dipole moment integral, transition dipole moment or transition dipole moment integral, uh, we found that it depends on the however the orientation of a molecule, how it depends on the and whatever the molecule is transition is strong or not, and selection, and eventually we got the selection rule. Now in the last lecture we found that we have started the some of uses of this whole calculation that we have done in the last 5 sessions. So today the theme of the tutorial is mainly based on rotational spectra and a little bit essence of vibrational spectroscopy. So let's start the assignment, and with the course with the progress we will see what we can do. Okay, so with this I am starting the session. Okay, let me share my screen. I hope my screen is visible, and let's start. So first question of the session is, for a diatomic molecule under rigid rotor approximation, the rotational Hamiltonian feature can be expressed as nothing but L square y. The correct statement among the following is or are is called the moment of inertia square is given by it is not theta, it is sine square theta. It's just a printing mistake. See, I is called the moment of inertia and is given by I mu r square, where mu is the reduced mass and Re is the equilibrium bond distance between A and B. D L square represents angular part Laplacian. Okay, so in case of rotational Hamiltonian, the Laplacian delta square integral is nothing but represent the total angular part. So this is total angular momentum. And IE is moment of inertia, which is nothing but mu r square, where mu is reduced mass. So with this option is incorrect. Okay, so now what is the expression of L square? So what we know previously, L is R cross P, and L square is Lx square, Ly square and Lz square. Now if we write the expression of Lx, Ly, Lz in Cartesian coordinate, it will be nothing but minus IH cut YPZ minus ZPY minus IH cut ZPX minus XPZ and minus IH cut XPY minus YPX. Now this is in Cartesian. So if we convert into spherical polar coordinate, so it should be like this. So this is something r dependence theta and phi. So or you can rearrange this thing. So with this it can be written as x is equal to r sin theta cos phi, y r sin theta sin phi, and z is nothing but r cos theta. Now if we incorporate all these value to Lx, Ly and Lz, you will get the value for Lx is nothing but Lx will be IH cot sin phi d by d theta plus cot theta cos phi d of d phi. Ly will be IH cot cot theta sin phi d by d theta cos phi d by d theta, and Lz will be your minus IH cot d by d phi. Now if we take the square of all, so you can think that L square is equal to L into A. So it is nothing but Lx dot Lx Ly into Ly, because all other terms are mutually orthogonal. Okay, so for that you will get the whole value. If you calculate, then you will get this value. The whole thing is carried out. You can do it by yourself, or it can be seen in any standard textbook. Okay, so this is the final version of the total angular momentum. So you can write it like h cot square one by sin theta this is the expression of L square. So this is a correct option. Just there is a printing mistake, that is not theta, it is sin square theta. Now third option is I is called the moment of inertia, that is a correct one, and given by mu r square, where mu is the reduced mass and Re, there should be, I should Re is the equilibrium distance. That's correct one. So this is a correct statement. Now L square represents the angular part of the Laplacian. It is correct. It is a correct one. So moving to the second question. The wave function of a diatomic rigid rotor is given by spherical harmonics y l m theta and phi. The correct statement among the following is or are: A. Y L M theta phi are eigen function of L square and Lz, where L is the total angular momentum and is the component momentum. B. Y L, sorry, it's not L, it's written, what is L or J? M theta phi are eigen function of L square and zero. C L square y z m theta phi is h cut square j plus 1 y j m theta phi. D L z y j m theta phi is h cut j y j m theta phi. So let's see one by one. The yjm are eigen function of L square and Z square. Yes, L square and Lz, where L, that is a correct one. Now yj is eigen function of L square and Lz. Yes, that is written in the first option. And we know if the two operators shares the common base eigenfunction, then they must be commute with each other. Okay, so this option is not correct. So question, question is written is not equal to, so this option is incorrect. So the actual thing is that if two operator, yeah, okay, to test this we can do like this. Otherwise, let's have a look on L square Lz. Okay, so L square we can written as Lx square Ly square Lz square comma Lz. So what we will get for this case, no, or you can it can be right like this, or it is something sorry, can do. I just tell you the recipe to do that. Maybe I have discussed it beforehand. Lx square Ly sorry. So it is Lx square plus Ly square plus Lz square Lz plus Lz Lx square Ly square Lz square. So it can be written as Lx square Lz Ly square Lz Lz square Lz minus Lz Lx square Lz Ly square Lz Lz square. So if you take these two terms Lx square Lz square and Lz Lx square, so you can write this thing like Lx Lx Lz Lz Lx Lx. Now if you add LZ, LX, LZ, and subtract it. Then you should get, after doing all this thing, so this value is nothing but LX to LZ, so which is nothing but LX, LZ, and this is also LX, LY. So if you take LX and LZ, it will give you, sorry, why it is coming. So it is LX. Similarly, the other term L square Z and LZ LY square will give you plus IZ LX LY LZ. So if you take the summation, then whole term will be nullified and you will get L square LZ value is 0. So it is also an way to do that formula. So this is a, so this term should be, so L square LZ must be 0. And now, so if we use L square operator on yj wave function, rotational the wave function in spherical harmonics, you will get nothing but the j into j plus 1 into h square term. But if you use the z component, so this is the correct one. So if you use the z component of y, j, m, theta, phi, then you will get the projection along it. J. So this is incorrect one. Okay. So like this. We have done with the second question. Let's look at the third number. For the wave function y, z, m, theta, phi described in question 2, the following eigenvalue equation given H rot yjm theta phi E rot jm yjm theta phi. The correct statements among the following is or are: the energy eigenvalues are dependent on the quantum number J and M. B. The energy eigenvalue is independent of quantum number M. C. The energy levels are non-degenerated. T. E dot Jm Hb J into J plus 1, where E is known as Shannon constant. So we start with this. We will get, so H rot yj theta phi is E rotational jm yjm theta and phi. Now E rotational jm is nothing but j into j plus 1 h cut square by 2y. Okay, so you can see E rod doesn't depend on M but depends on J, where J is from 0 1 2. Okay, so this first option is incorrect. Now therefore energy eigenvalue independent of M. Okay, now the energy level. So if we take the degeneracy of rotational levels for diatomic molecule, Gj is 2j plus 1. Therefore, the labels are not non-degenerated. They has a degeneracy, and they are 2j plus 1 fold degenerate. So for j is equal to 1, you will get 3 degenerate rotational state. J2 it will give you 5 and so on. So this is also incorrect. Now as I mentioned, E rod J m is j into j plus 1 h cuts by 2I. Now it can be written as h by 8 pi I into j plus 1. Now if we write B as a h by 8 pi square I, then it will be h b j into j plus 1. Now B is nothing but known as rotational constant. Okay, which has a expression h by okay. So P is rotational constant. So this is a correct one. Now let's move to the question number 4. So let's see what it asks. In question number 4, So we can see that for a molecule to have pure rotational spectra, it must have dipole moment. If it doesn't have dipole moment, it cannot sense the electric field. And so therefore, if you take the molecule like O2, H2, this molecule doesn't process any uh, dipole moment, and therefore non-polar molecule and any uh, like O2, H2, these are doesn't exhibit so pure spectra. Okay, so see, so molecule should be polar like water, ammonia. These can show rotational spectra. This is the correct option. Now mu is equal to 0 is not a then you will not get anything. So this is incorrect. Now if you think a molecule AB is like this, where A side is delta positive and B side is delta negative, then the direction of the initial dipole moment would be like this. Now if light passes through in this direction, so this is case 1. So direction of electric field is perpendicular along the direction of permanent dipole moment. So in that case, the TMI will be 0, because mu is nothing but mu into E. Okay. Now in case 2, another case, if this electric field is propagate like this, so del E, therefore TMI will have a finite value. Okay, so for in this case, rotational spectra will observe. Here no rotational spectra. So your molecule for a polar molecule, the the electric field should be like to get the rotational spectra, the electric field must be perpendicular to direction of the dipole moment. Otherwise, or there should be some projection of electric field with the dipole moment. Otherwise, if it perpendicular to the direction of dipole moment, then you will get no rotational transition. Okay, so correct option. So TMI should not equal to 0 to observe the rotational spectra. That is correct. If TMI goes to 0, then there should not be any transition. Now question number 5. The correct statements So the first option is correct because for a rotational transition you need delta J plus minus 1 and M value is 0. Now intensity of rotational transition is independent of the degenerate of the state. So now what we know, intensity actually proportional to the population of state. Now in Boltzmann distribution you can write population of J state with respect to J is equal to 0 state is nothing but where delta Ej is difference between J level and the 0th level. So therefore if we say the population of the state determines the intensity, then what is done, this is nothing but degeneracy. So degeneracy, therefore degeneracy intensity of rotational transition is also depends on degeneracy of state. So second thing is not, is written over the intensity of transition is independent. That is not a correct statement. The rotational spectra shows P bands, whereas Q branch are missing due to selection rule. So what we say, the selection rule what says, transition can happen only J plus minus 1 and M value is 0. So if we record the spectra, so there should be a J is equal to plus 1 side. Okay, so now if you record the spectra, it will be like so this is, you can think and so on, and this is the minus signs. So it is like that only. So this is the 1 to 0, 0 2 to 1 like that. So these branches are P, and this is, there should be a one band which is something Q branch, which is forbidden as it says delta is equal to 0. Therefore this Q branch is totally absent in pure rotational spectra due to selection rule. So this is a correct option. Now values of J max remain same. So J max means, see you can see this plot. So once it started going up, so you can think So if you look at that, so this thing is starting up to 3 to 4 and then it's come down. Okay, so this area you can is J max. Now the J max actually depend on for a particular, for a given molecule. Actually J max depends on the rotational constant and temperature. Okay, but for a particular, for a given molecule, so J max is only depend on temperature. So if the temperature rises, so the you can do like this, Nj exponential so you can think that Nj N0 2j plus 1 exponential b to j into j plus 1 kBt. Now take the derivative and make it 0, then you will get a expression of J max. Which will be nothing but, let's do it, dnj plus dj. So is equal to 0. So you can think is 2 exponential b j into j plus 1 by kBt, okay, plus or minus okay, b 2j plus 1 by kBt exponential b j plus 1 by kBt. And there is a 2j plus 1 square term is before. So what we will get at, so this term will be 0 at J max. So what we will get, 2 b 2j plus 1 square by kBt. There is a h term. Equal to 0. So now we can add J max. So J max is kBt by 2 h b minus half. So this is the expression of J max. So if J max depends on T. So it's not a it's not a independent thing and not a constant. It also depends on a temperature. Okay, so with this is also a incorrect statement. So now moving to question number 6. So the correct statement respect to rotational spectroscopy of a non-rigid rotor molecule is or are a rotational lines are evenly spaced for all the J values. In case of non-rigid molecule. B, with increasing J value, bond distance also increases in case of rigid rotor molecule. With increasing J value, effect of centrifugal distortion constant Tg becomes negligible on the spectrum of the in case So till now we have discussed about molecule as rigid rotor. So what does a rigid rotor means? If a molecule A and B like this, their distance is always fixed and the corresponding energy to be found is J H into B. Now this is not ideal case. So when a molecule start rotating at a certain J level, the molecule start feeling outward what I can say outward attraction outward force. So therefore the molecule now same size. Now the molecule gets some centrifugal distortion. Therefore now the R is the distance R is no longer fixed. Okay, so the rigid rotor approximation fails here. Now in such a case the EJ is written as you can take BH as a BE. Okay, 1 minute. So HB you can take as a B. Okay, J into J plus 1. So this B is nothing but H into B. You can take a BE. So this thing at non-rigid rotor approximation, it will be J into J plus 1 minus D J. So this is centrifugal distortion. Now so with the increase of J you will see increase of bond distance. So this is it's like you are the molecule feels more and more distortion on increasing the bond length. It's straightforward. So now we can write, so this option, so now if you take for rigid rotor case, you will get all the lines. So you can take this first one is nothing but 0 to 1 is 2B, next one is 4B, 1 to 2. So 1 to 2 is in rigid order of 6B minus 2BE, that is 4BE. Now in the rotor approximation, 2 to 3 is nothing but 3 into 4, 12BE minus 6BE, 6BE. So this is will be 8BE. So all the lines you can see equi-spaced, but for let's do it for non-rigid case, non-rigid rotor case. So if we take 0 to 1 transition in non-rigid rotor, so what will happen? BE will be, so 1 into 2 minus D 1 square 4 square minus everything will be 0. So the term will be BE minus 4DE. Okay, now if I take 1 to 2, for 1 it will be, for 2 it will be 2 into 3 minus DE 2 square 3 square minus BE plus 4DE. So it will be 6BE minus 36DE minus BE minus 4DE. So it will be 2. It will be 4BE minus 32DE. Now if we do it for E2 to 3, now what we will get? BE 3 4 DE 3 square 4 square minus 4BE plus 32DE. So what to remember? 12PE minus 16 and 9 will be 144. So 8BE minus 112DE. So now if we comparing rigid rotor versus non-rigid rotor, then what we can see, this is 0 to 1 as 2B, 1 to 2 is 4BE, and 2 to 3 is 6BE. sorry, this will be correct. This will be 6BE plus 36DE. So this value will be 6BE minus 108DE. Okay, so now it's okay. So all the lines are equispaced by 2BE. Now if we write, what will be the case? So first case, it's decreased by 4DE. Array. So first thing, this line is decreased by 4D. Okay, so this is 2BE minus 4D. Now secondly, this is decreased by 4BE minus 32. So 4BE plus 32DE. So this gap becomes now 2BE minus 28DE. Now this one is decreased by 108. So this is 6BE. So this line is decreased by 2BE minus 76DE. So now on going to rigid rotor to non-rigid rotor, you can see that the equispacing what we observed in rigid rotor is not conserved in case of non-rigid rotor molecule. So therefore this option what it says, with increase so that is already written, with increase the J value, effect of centrifugal distortion DE become so now with this we can say that so line becomes more and more closer, so the equispacing is not there, so this option is incorrect. Okay, now what's with increase in J, the effect of centrifugal distortion constant becomes negligible on the rotational spectrum of the non-rigid rotor molecule. So now you can think that a D value, the value of D is much smaller than B, and whereas the equation says so DE is 10 to the power minus 4 of BE. So if to get DE significant, so J value must be high, of the order of 2 digits. Therefore the DE is negligible, but to get the effect of value of DE, the J value must be increased, otherwise it will not observe. So with increasing of J we cannot you cannot neglify the DE value, so this option is incorrect. So the effect of centrifugal distortion is much more pronounced. So let me write the effect of centrifugal distortion much more pronounced at higher J. Now, in case of non-rigid rotor molecule, in case of delta E 01 is greater than delta E 12 greater than delta E. You can see that we can derive that this value is getting diminished by the distortion value. So this is the correct option. Okay. With this, let's move to the option number 7. The correct statements about rotational constant B for a linear molecule among the following either with increasing value of P, value of J max also increases for molecule having permanent dipole moment. B, value of B remains constant irrespective of the bond length of the molecule having a permanent dipole moment. C, value of B decreases with increasing bond length of the molecule having permanent dipole moment. T, for a rigid rotor molecule, rotational transitions are separated by twice of B. Now as I derive few more slides back, what is the expression of J? It's nothing but J max is KT by 2HB minus half. So if B value increase, then J value will be decreased. Okay, so with this, with increasing of B, the value of J max will also increases. It's a incorrect option. Now the question said value of B remains constant irrespective of bond length of the molecule having of a molecule having permanent dipole moment. Permanent dipole moment is okay because it's needed for to see rotational spectroscopy, rotational spectra. But the expression of rotational level is J into J plus 1 H cut square by 2I. Okay, where it properly written is like 8 pi. So our convention is to write it like J B J into J plus 1. So where B is known as rotational constant and its expression is H by 8 pi I. Now I is moment of inertia, and it depends on mu. It is mu into r square. R is the bond length and mu is the reduced mass. So if A and B forms rigid rotor molecule, then this will be the distance. So this is the R and mu will be MA into MB plus MA plus MB. Okay, so therefore the expression of B can be written as, so B is nothing but 1 by r square. So rest of the term is constant for a given molecule. So B is inversely proportional to square of bond length. So the value of B is not fixed. Okay, so this option is also incorrect. And if R is increasing, then B will be decreasing. So B value decreases with the increasing of the bond length. That is a correct one. Now the last question is said the rigid rotor molecule, the rotational transition are separated by twice of B. So we know that for E, so if we take transition from, so what we can write, H B J prime, sorry, J is the final state. And rigid rotor approximation, the selection rule is this. So if we take 0 to 1, you will get the value 1 to 2, 2 to 3, So all are is twice of B. You can take H into B as a B. It's depend on the whatever the convention you are using. So this option is also correct. Now question number 8. The correct statements of So let me take. So now we have come into uh, vibrational thing. So now let's start this little bit simple description. So for a rigid rotor, the bond length rigid rotor, the bond length is always fixed. Therefore, there should not be happen there for a for a rigid rotor, the reaction will not happen. Any reaction will not happen. So no one will survive. If bond breaking or bond making is not taking place, then there is no question of living. So the non-rigid rotor approximation is a very unreal thing. So non-rigid rotor case is the much more fundamental and applicable to real systems. So in non-rigid, so if we see the potential energy curve for rigid rotor, you can see like this. So bond will not dissociate, and this is follow harmonic potential. But in non-rigid rotor case, your potential will no longer like the same. It will be something like this. So if we write the levels, you can start seeing that the bond is breaking after a certain vibrational level. Okay, so there comes anharmonicity. Now if I think about the bottom of the well, so it's something like this. It is sorry. Only and so this was harmonic and this is anharmonic. But one thing should be noticed that at the bottom of the well, anharmonic becomes harmonic. Okay, so bottom of the well, you can think anharmonic thing as a harmonic one. Okay, so therefore let's see the first option. Complete potential surface curve of a non-rigid rotor molecule can be approximated as a harmonic potential. So complete is cannot be. Only the bottom of the well can be treated as a harmonic potential. So this is a incorrect. And I can see that only the bottom of the potential energy curve of a non-rigid molecule can be approximated as a harmonic potential. It is a correct option. Now the third option is a complete potential energy curve of a non-rigid molecule can be approximated as a harmonic oscillator as the bond distance remain constant at higher vibrational potential. So I mentioned that with the increase of the vibrational levels, these are the vibrational levels, you can see the bond distance is increasing. So now the molecule is no longer in harmonic case. So V increases harmonic V increases harmonic approximation becomes invalid. So this is not a correct option. Now the thing is that at the bottom of the potential, the energy curve of non-rigid rotor molecule can be written as V is equal to kx square. So then V can be written as V0 minus dV dx measured at x equilibrium, x plus dV2 dx2 measured at x equilibrium, x square and 2 factorial and on. Okay, higher order term can be neglected. Now so we can written as now in quantum mechanics the energy is measured with respect to some energy values na. So the energy is measured with respect to VE. So you can take VE as 0. So the thing is coming like this. So the EA is that the energy is relative to V0. Now at the bottom of the potential, that means it's a minima. So we know at minima this thing should be 0. So nothing but becomes x square. Now this thing is denoted by some constant known as k. So k, f or k, whatever. So this is known as force constant. So details of this force constant and all will be discussed in the next session. Okay, so it can be written as ax square. Okay, so this option is correct. Now moving to the last question of the session. For a linear diatomic molecule AB, nuclear Hamiltonian HN is given as HN HCM H internal. So HCM is motion around center of mass and H internal of molecule A. A molecule AB is a non-rigid rotor. B molecule AB is a rigid rotor. C represents a free Hamiltonian. D internal structure molecules are C. So as I know, I have told it that the molecule should be non-rigid rotor. So you can just quickly choose option A as a correct option, and as a option A is correct, then it should not be rigid rotor. Now delta HCM. So HCM, Hamiltonian CM, represented a motion, translation motion with respect to center of mass. So therefore, but one thing to notice, the Hamiltonian with respect to center of mass doesn't have any potential term included into it. Therefore, as you see, particle in a box, within the box there is no potential. So this kind of particle is called free particle. As in delta, similarly in delta HCM, HCM doesn't have any potential. We can consider this delta HCM actually represents the free particle Hamiltonian. Now the internal
but here, excuse me sir, but
yes,
but here is that we consider that the potential is 0 in case of particle in one dimensional box, but here it is not 0.
Why? Because see, it's written about HCM, not H internal. HCM doesn't have any potential energy term. It's only translation motion along the center of mass. Okay, if there is no potential, the molecule behave as a free particle. So if you consider the HCM, as there is no potential, it must consider as a free particle Hamiltonian.
Yes sir. Okay.
Is it okay? Okay. So the delta square CM, there is no what is this? There is no potential. Therefore, it only shows the translation along the center of mass. So it doesn't take about anything about the internal structure of the molecule. So with this, we can tell that this option is also incorrect. So it's just a motion along the center of mass. So it doesn't incorporate anything about the molecular structure, and therefore the measuring of the change with respect to center of mass is not so easy. Okay, so with this this thing is done. Assignment 6. So for next session, the tutorial, the class will be on vibrational vibrational spectra, selection rules, and and electronic excitation. Okay, so we have completed the today's session. If you have any question, you can ask.
In case of rotational spectra, we get the selection rule as delta J is equal to plus minus 1
Yeah.
and delta M is equal to 0.
Yes.
But why not delta J plus minus 2?
If you derive the full equation for uh, you can take any say SAT has done up to this full derivation is not done na. It's in homework. You can see any standard textbook, what Atkins molecular spectra. You can see only the transition, the Hamiltonian is only valid when the see if you take, I can tell you how is actually comes. This is only valid when you can see that if you take the okay, so if is j dash to j prime, the Hamiltonian will survive when the j prime minus j value is 1. You will get a something Kronecker delta, where you will see that this value is only survive when, sorry, something like that, j double prime will be plus 1 and j double prime minus 1. So from there it concluded, and also for m value it will be 0, otherwise it will not survive. From this thing they actually concluded this one. So details things, it's written on the Atkins is okay. It's written on Atkins only. You can just look at the Atkins spectroscopy or Levine. Okay, so it's a quite a bit long calculation. Okay,
Okay, thank you.
you can do it as a homework, as Sir also mentioned, but yeah, you can get the same answer in whatever method you apply. Okay. Anything else?
No, sir, I have attended it's a different class.
Okay.
So I could not attend this
Okay.
earlier.
Okay.
I will go through
Okay.
the recorded list.
Okay. Anyway, let me stop it here. Okay, bye.